For 100 years, the rules of the automotive world were written in steel and fire. If you wanted more power, you needed more displacement. If you wanted more speed, you needed more fuel, more explosions per second, more heat pouring out of a block of metal that would eventually wear itself down no matter how well it was built. Every engineer who ever designed a combustion engine lived inside that trade-off because there was no way around it. Power cost you something. It always had. Then a small design change buried inside a motor most people will never see quietly broke that rule. And almost nobody outside the industry noticed when it happened. The car it lives in is the Tesla Model S Plaid, and on paper it already sounds like fiction. 3 electric motors work together to move the car, 2 mounted on the rear axle, 1 on the front, and combined they produce more than 1,000 horsepower. The Plaid accelerates from a standstill to 60 miles an hour in roughly 2 seconds. Not 2.5, not close to 2. Right around 2 seconds flat, a number that used to belong exclusively to million-dollar hypercars built by companies whose entire reputation rested on that single figure. The Plaid's top speed sits near 200 miles an hour in a car with 4 doors, a trunk, and space for your groceries. Numbers like that usually come with an asterisk, a carbon fiber body to save weight, a stripped interior, slick tires that wouldn't survive a rainy commute. The Plaid doesn't need any of those compromises, and the reason comes down to something most drivers never think about. What's actually happening inside the motor itself while the car is doing all of this. Traditional electric motors are limited by how fast their rotor, the spinning part inside the motor, can physically turn before it starts to tear itself apart. Spin something fast enough, and centrifugal force starts fighting against the very materials holding it together. Engineers have known this limitation for decades in electric motors and combustion engines alike. There is a ceiling, and past a certain point, going faster stops being an engineering problem and starts being a physics problem. The kind you can't outdesign your way around with clever tuning. Tesla's engineers went after that ceiling directly. The motor at the heart of the Plaid was developed in-house, from scratch, and one of its defining features is a carbon fiber sleeve wrapped around the rotor. That sleeve isn't decorative, it's structural. It holds the spinning rotor together at speeds that would cause a conventional design to fail, letting the motor spin at dramatically higher revolutions per minute than anything Tesla, or arguably anyone else building street-legal motors, had produced before. Higher RPM translates directly into more usable power, without needing a bigger, heavier motor to get there. It's a quiet piece of engineering, easy to overlook next to a headline number like a 2-second sprint to 60, but it's the actual reason that number is possible at all. This matters more than it might seem to at first, because it changes the entire conversation about what an electric powertrain is capable of. For years, the assumption baked into public conversation about EVs was that they were efficient, clean, and quick off the line, but not necessarily the top performers in an outright horsepower fight. That assumption was already outdated before the Plaid, but the Plaid made it impossible to ignore. A carbon-wrapped rotor spinning at extraordinary speed isn't a compromised version of a supercar. It's a different approach to the same problem. Combustion engineers have wrestled with for a century, arriving at a number combustion has essentially never touched in a production vehicle, let alone a full-size sedan. The clearest evidence of what this motor is actually capable of doesn't come from a spec sheet. It comes from the street. Videos have circulated of Cybertrucks, heavier, less aerodynamic, built for hauling rather than racing, beating Lamborghinis in straight line drag races. To anyone raised on the assumption that supercars win those matchups by default, the result looks almost like a glitch. It isn't. Electric powertrains deliver their torque instantly the moment the accelerator is pressed without waiting for gears to shift or revs to climb the way a combustion engine has to. Paired with a motor capable of spinning as fast as Tesla's new design allows, that instant torque translates into acceleration figures that simply weren't available in a mass-produced vehicle before this generation of motor existed. None of this happened by accident, and it didn't happen quickly either. Tesla has always positioned itself as a company willing to build the car other manufacturers assumed wasn't worth building. Long before Plaid, long before the current wave of high-performance electric vehicles, the company built limited, run sports cars aimed squarely at proving electric power could compete with, and eventually beat, the fastest gasoline engines on the road. For a stretch of time, that ambition took a back seat to different priorities. Mass-market vehicles, affordability, expanding the charging network that made owning an EV practical for an ordinary driver instead of an enthusiast with a garage full of specialty tools. The high-performance ambition never disappeared. It resurfaced with the Plaid motor, and by every indication available, it isn't finished resurfacing yet. Elon Musk has said directly that the carbon-sleeved motor built for the Model S Plaid is the most advanced motor currently sitting inside any street-legal vehicle, and that the same underlying technology, refined further, is intended for the next generation roadster. If that turns out to be accurate, the Plaid's numbers, as absurd as they already sound, may end up looking like a Starting point rather than a ceiling. A 4-second plus quarter mile from a full-size sedan was, until recently, the kind of number reserved for specialty drag cars stripped of every unnecessary pound. Now it's a number attached to a car with air conditioning and a back seat. It's worth pausing on why this particular engineering choice, a carbon sleeve around a spinning rotor, ended up being the detail that unlocked all of this, instead of some flashier, more marketable innovation. The answer is almost frustratingly simple. The limitation was never really about power in the way most people imagine it. Batteries can deliver enormous amounts of energy in short bursts. Software can manage that energy delivery with extraordinary precision, timing it perfectly across 3 separate motors working in coordination. The bottleneck was mechanical. It was about how fast a physical object could spin before it broke. Solve that one narrow mechanical problem, everything downstream of it, the acceleration, the top speed, the seemingly impossible drag race wins, becomes achievable, not through some radical rethinking of what an electric car is, but through solving the boring, unglamorous physical constraint standing in the way. That's often how real breakthroughs work, and it's part of why this story doesn't get the same viral traction as flashier claims about secret engines or impossible fuel sources. There's no mystery here, no hidden protocol, no forbidden technology being quietly unveiled. It's a team of engineers identifying a specific physical limitation, addressing it directly with a specific material solution, and then letting the resulting car speak for itself on a drag strip and in an acceleration figure that used to belong exclusively to cars costing many times more. For drivers who grew up associating performance with noise, smell, and vibration, the visceral experience of a combustion engine working hard beneath them, this new generation of electric performance can feel almost eerie. The Plaid doesn't roar. There's no exhaust note climbing in pitch as the revs rise, no shudder through the chassis as the engine strains against its own limits. There's just acceleration, immediate and continuous, delivered in near silence, which is part of why so many first-time passengers describe the experience less like driving and more like being launched. The absence of the traditional sensory cues doesn't mean the power isn't real. It means the power is being delivered by a fundamentally different mechanism, one without the decades of cultural association combustion engines carry with them. Skeptics inside the traditional automotive world have been slow to fully embrace what this motor represents, and that reluctance is understandable, given how much of performance car culture is built around combustion. The sound of a flat-plane crank V8, the ritual of a manual gearbox, the decades of motorsport history tied to internal combustion racing. But reluctance doesn't change outright numbers. A production sedan running a sub-2-second 0 to 60 and beating dedicated performance vehicles in straight-line competition isn't a marketing claim that requires faith to accept. It's a repeated, documented, publicly witnessed result, achieved by ordinary buyers driving cars they purchased off a lot, not prototypes, handled exclusively by factory test drivers under controlled conditions. What makes this motor worth paying attention to isn't just what it's already done, but what it signals about where the ceiling actually sits. For 100 years, the assumption in the automotive industry was that outright power and everyday usability existed in tension with each other. You could have blistering acceleration, or you could have a comfortable, practical car, but rarely both without an enormous price tag attached. The Plaid's motor challenges that assumption directly. It's not a stripped-down track special. It's a full-size luxury sedan that happens to outrun cars costing 3 or 4 times as much, built by a company that, according to Musk's own public statements, considers this specific motor design a stepping stone rather than a final destination. If the next Roadster genuinely inherits a refined version of this technology, the implications extend well past bragging rights on a drag strip. It would mean the physical constraint that limited electric motor performance for years, the mechanical ceiling on how fast a rotor could spin before failing, has been meaningfully pushed back, with real headroom left to push further. It would mean the era of treating combustion engines as the default benchmark for outright performance is closer to ending than most casual observers currently assume, not because of a single dramatic announcement, but because of a carbon fiber sleeve wrapped around a spinning piece of metal, quietly doing exactly what it was designed to do, thousands of times a minute, every time the car pulls away from a stoplight. None of this required secrecy to be impressive. It didn't need an insider leak, a whistleblower, or a mysterious video shot from an anonymous source. The information has been public for years, sitting in spec sheets, engineering explanations, and interviews, available to anyone willing to look past the headline number and ask the more interesting question underneath it. Not how fast is this car, but why is it able to go this fast at all? The answer turns out to be smaller and more specific than most people expect. A material solving a narrow mechanical problem, unlocking a broader outcome nobody had achieved in a production vehicle before. That's usually how the real story compares to the version built for clicks. The real version doesn't need an exaggerated title or an invented number attached to it to hold attention, because the actual engineering, examined honestly, is already strange. Enough. Already impressive enough. Already worth explaining carefully instead of breathlessly. A four-door sedan running acceleration numbers that used to belong exclusively to million-dollar hypercars isn't a rumor. It's a documented fact. And the explanation behind it is a story about material science and mechanical constraints, not about hidden agendas or secret unreleased technology waiting to be exposed. Where this goes next depends largely on how far Tesla is willing and able to push the same underlying approach. Motors capable of even higher rotational speeds, wrapped in even more advanced materials, paired with battery chemistry that continues to improve year over year, suggest the current numbers, as extreme as they already sound, aren't necessarily close to the practical limit of what's achievable in a road-legal vehicle. Whether that next step arrives in a future roadster, a future performance sedan, or some vehicle category that doesn't fully exist yet, the underlying lesson from the Plaid. Motor is likely to hold. The biggest leaps in performance don't always come from a single dramatic invention. Sometimes they come from identifying the one specific, unglamorous constraint standing between where you are and where you want to be, and then simply solving it, carefully, deliberately, one carbon fiber layer at a time. That's the actual story behind the motor everyone keeps trying to turn into something more mysterious than it needs to be. Not a secret, not a conspiracy. Just an engineering team that looked at a 100-year-old limitation, decided it wasn't permanent, and built something that proved it.